All right, hello class, and welcome to Lecture 7. So Lecture 7 is the final part, I guess, of what you could call the first part of this class, where we've completed the arc, where we're able to determine our orbital elements, propagate them forward in time, and make predictions on where exactly this planet or the spacecraft or whatever it is that we're chasing is going to be. Now, in the second part of this course, we're going to start moving things around. So we'll talk about the Hohmann transfer and how to navigate in space, orbital. And then in lecture 14, actually, we're going to come back to interplanetary trajectories. But before we get there, right, we have to do our homework, eat our vegetables, and that requires to complete this arc. And so I'm actually going to break this lecture down into 4 relatively brief parts. The first one is going to sort of summarize everything we've learned so far in this course. So in particular, we're going to be going from position and velocity, measurements of position and velocity at some initial time, to the orbital elements at that initial time, a semi-major axis, eccentricity, right ascension, inclination, argument to periaps, and true anomaly. Then we will go to, of course, E, eccentric anomaly, M, mean anomaly, and from thence to time, which we already knew. But we have M of T naught, that's important. And then we're going to add a delta T to that and go back the other way, getting M of T2, E of T2. All the orbital elements except F will be the same, but F will change, T2. And then finally, as that's where we'll stop in part A. And then finally, in parts B and C, we're going to be able to find R of the vector T2 and V of T2. Okay. So this last little leg right here is going to be this lecture, parts B, part C, and then finally in part D, we'll talk about pointing angles, so right ascension and declination. Not right ascension of the ascending node, although of course the concepts are related. Just indicate here that these are frozen elements. Don't change. So, well, let's get started then with summarizing everything other than that last step, right? Which is part A. Right. So that's this slide just summarizes what I was just talking about. And then this slide gives just a sort of a more practical interpretation of what all this means once we've completed the arc. So in particular, say I make an observation with my telescope of a celestial body or a spacecraft or a satellite at some particular time, t1, and I observe it has position and velocity vectors thus. At T1. I want to be able to predict what are going to be the position and velocity vectors at 3 o'clock. So if I observe it at noon, where's it going to be at 3 o'clock? So to do this, we've got to, of course, calculate the orbital elements at our initial time, propagate our orbit. This, of course, is going to be that's from lecture 6, and of course lectures 1 through 3. And then we're going to propagate the orbit using the stuff in lectures 4 and 5. And then finally, we're going to use the stuff in lecture 7, which I haven't talked about yet, to be able to compute those final position and velocity vectors. So the first part A here is going to be summarizing steps 1 and 2, and then the parts B, C, and D will summarize or derive step 3 now. Just I guess a quick word, right? That this last step, right, is conceptually quite challenging. It's very different than what we went through in lecture 6, where we were determining the orbital elements given the position and velocity vectors. Go here, there. Right. So there was a huge sequence of steps that we went through to get those 3D orbital elements. Going back the other direction, however, requires some additional, let's say, mathematics, right? It requires rotation angles because we're going to be rotating vectors. And so what we're going over in lecture 7 is actually very much different than what we went over in lecture 6. So don't think that this is a simple application. Although when we get to the end, there is actually a formula that we give for these orbital elements, for the position and velocity vectors, just directly expressed in terms of those orbital elements. I think I can actually dig. Where is it? Somewhere over here. Yeah, there it is. So we can directly actually have a closed form solution for this position and velocity vector in terms of those orbital elements. But understanding this big, huge, hairy equation, right, which is, of course, a major result, requires us to go through a lot of rotation matrix stuff. So we'll have to do that. Right. So just a quick word on the presentation in lecture 6 versus the presentation, another difference between the presentation in lecture 7. In lecture 6, I defined the rotation of that orbital plane, right? So we had this 2D orbital plane where we have a central body. We had the eccentricity vector defining periaps, angular momentum vector defining the normal to the orbital plane. And so I define that in terms of first a rotation actually about the x hat vector. So I was defining these rotations in sort of the ECI frame, where in fact in this lecture we have to stick with the perifocal frame. So I'll try and explain that difference. So in the first case we had a rotation about by the inclination about the x hat axis. And then we had a rotation around the z hat axis to give us the right ascension. And then we had a rotation around the angular momentum vector to give us that third rotation, get our periaps up into the right position. Unfortunately, that's not the approach we take in this lecture, because these rotations that I just described don't correspond to the standard rotation matrices. In particular, if we did the inclination rotation first, right, then the instantaneous z hat axis is always coinciding in the perifocal frame with the angular momentum vector, and then it doesn't make sense to rotate around the z hat axis because we can't use the R3 rotation matrix because it doesn't align with our instantaneous z hat axis. And so we've got to do this in a slightly different order. First, we rotate about the z hat axis, right, which coincides with the perifocal frame, because remember we're initially had this alignment with the eccentricity vector in the x hat and the angular momentum vector in the z hat. So instead we're going to initially rotate about the z hat by the right ascension and descending node, so that the eccentricity vector is aligned with the line of nodes, Then we're going to rotate about the line of nodes. That's an R1 rotation. This is an R3. First one's an R3 rotation to get us up there. And then we're going to rotate around the angular momentum vector, which is, again, right, the z hat, but no longer aligned with the true z hat direction in the ECI frame to get that periapse up there. So that's going to allow us to do a 3-1-3 rotation and use our standard rotation matrices instead of having to custom define rotation matrices. So as I said, rotation matrices are a little bit subtle. So hence we're actually going to have a whole part B on that. If you feel really comfortable with rotation matrices, you can skip part B. But again, I don't advise it. Right, so as I said, as I promised, I guess, we're going to go over our steps, basically the entire lectures 1 through 6, which allow us to take position and velocity vectors and first find our orbital elements, A, E, omega, true anomaly. And then we'll talk about getting eccentricity at T1, mean anomaly at T1, go to delta T, mean anomaly at T2, then back to E of T2, then back to F of T2. And there we'll stop, because parts B and C will cover this last step, getting R and V at future time. Okay. So let's get over it. So as I said, you start with the position and velocity vectors at some initial time. T1 actually, I guess I'm using. So what do we do with them? Well, first we calculate our angular momentum vector, our first invariant element, right? Remember that from lecture 1. Lecture 2. Then we find our line of nodes by crossing the z hat axis with the angular momentum vector. Right? Technically, that's a little bit out of order because that was in lecture 6. Then we find the eccentricity vector. Right? Again, that was lecture 2. That was our second invariant of the orbits, or was that lecture 3? No, that was lecture 2. Again, right, using cross products on the angular momentum vector. Here's R and V, right, where that comes in. R, V. Actually, let me use a different color there. Right. Angular momentum vector pops in there, and then it also pops in there. Alternatively, if we really don't like calculating the angular momentum vector, or we really don't like using cross products, there's actually a very interesting formula for eccentricity vector defined directly in terms of R and V. So we can actually skip that step, possibly. So in particular, it expresses the eccentricity vector as a combination of R and V, which are both in the orbital plane. And the coefficients are given by these two equations here. So there we go. Now we take that eccentricity vector, and of course we find its magnitude to find our first orbital element, which is E. Just for convenience, let's go ahead and define some other things here: the magnitude of velocity, the magnitude of position, and the magnitude of angular momentum. Now, as you may recall, right, angular momentum can be converted directly through that physical invariant to the parameter, h squared over mu, but that's actually not the approach we take in this summary. Rather, the approach that we take in the summary sort of emphasizes the direct nature of the R and V vectors to the orbital elements, and so as much as possible. And so here we actually calculate energy based on R and V, and then use our very convenient formula, which relates that invariant of motion energy to the semi-major axis, our geometric invariant. So now we have two orbital elements. Good. Let's keep moving. Now we're going to find the orientation, right, of that ellipse. We've got the ellipse, right, because we've got A and E. Now we have to find the orientation of that ellipse in three-dimensional space. Right, and so here we're going to use a lot of angle definitions, right? So angles to vectors, vectors to angles. And in particular, here we're going to use the third component of angular momentum, right? The rotation of that angular momentum vector gives us our inclination. So in particular, this is h3, the third component of angular momentum, divided by, of course, the magnitude of h. So that's just a fancy way of writing this bit right here. And then you calculate the inverse cosine of that, and you have your inclination. No quadrant ambiguity, remember, because inclination only varies between 0 and 180 degrees, and so we don't have anything to worry about here with quadrant ambiguity. So this is our formula for the second, or actually I guess third, orbital element now. Next, we go on to write essentially the ascending node. Here we have to use that line of nodes. And again, it's just the third component of the line of nodes divided by its magnitude. Here I use the magnitude to distinguish this from just n, which is, remember, mean motion. So again, right, we do that inverse cosine. We're finding the angle that line of nodes makes with the x-hat axis in ECI coordinates. And we do the inverse cosine. Now this line of nodes can vary all the way between 0 and 360. And so we do have quadrant ambiguity in this case. So we have to do a little check on quadrant ambiguity. Specifically, if the second component of the line of nodes is positive. This is, remember, the y-hat direction. So if it's positive, then this line of nodes, this angle it makes is between 0 and 180. So this is just n2 here. So if n2 is greater than 0, then we're good. We're in the right quadrant. If, however, that n2 is negative, then we're in the wrong quadrant. We're pointing over, the line of nodes is pointing over here somewhere. And so we have to do a correction. We take 360 minus the right ascension, and that gives us our corrected right ascension. So we just either plug that in there or plug that in there using this case logic based on the second component of the line of nodes. And that gives us our formula for right ascension, our fourth orbital element. Of course, we could have done true anomaly first, but since we have a vector version, I'll leave it to the last. Next, argument of periaps, right? So the argument of periaps, the formula is a little bit more complicated, but not too bad. So it's the angle that the eccentricity vector makes with the line of nodes. Right? Is our argument of periaps. And remember, the line of nodes is in the orbital plane. Is in the equatorial plane. So we have to do a little dot product there. And of course we divide by the magnitudes to get our standard cosine form, inverse cosine formula. So that's our next formula. Now we've got to do a quadrant check, right? So we have to determine if this eccentricity vector, remember we're at the ascending node, so we're orienting up, right, from the equatorial plane. And so if the eccentricity vector is in the northern hemisphere, this angle is between 0 and 180 degrees. So the descending node, that's 180 degrees. And so we just look at the third component of the eccentricity vector. And if that third component is positive, by definition of the ECI coordinate system, it's in the northern hemisphere. And so we don't have to do any corrections because we know we're between 0 and 180. If, however, that third component of the eccentricity vector is less than 0, that means the eccentricity vector points into the southern hemisphere, and so our periaps will be in the southern hemisphere. And so we have to do a little quadrant correction here. We're pointing this way, so actually we're measuring this, and so we've got to actually calculate that. And so we do that by doing 360 minus the angle to give us a little quadrant check there. So that this gets corrected or not based on this case logic. Finally, true anomaly, right? True anomaly, of course, represents where the angle that the position vector makes. Sorry, that's not position. With the eccentricity vector. That's true anomaly right there. And we can think about that in terms of this three-dimensional orbit, but perhaps it's a little bit easier to think of it in terms of the two-dimensional orbits. Here we go. There's the eccentricity vector in the orbital plane. Because both eccentricity vector and position vector are in the orbital plane. Okay. And so now we just use a standard cosine angle formula to find the dot product between r and e, and divided by the magnitude inverse cosine. Of course, we could have used the polar equation here, inverted the polar equation, right? To find a true anomaly, it would give us exactly the same number, right? Because there's still a quadrant ambiguity in this one, as well as this one. But since we're thinking in terms of what these vectors are in three-dimensional space, it makes, I don't know, some sense to use the vector version of this formula. Right. This time we, of course, do have to do a quadrant check. I think the quadrant check's a little easier to visualize in 2 dimensions, of course. Basically, we want to know whether the radius vector, the magnitude of this vector, is decreasing or increasing. So if it's increasing, we are in the first arc of the orbit. And if it's decreasing, we're heading out to apogee. And if it's decreasing, then we're in the second half of this orbit, headed back to periaps. So to calculate the r dot, we look at the alignment of the velocity and position vectors. So if r dot v, for example, makes an acute angle, we have r dot greater than 0. And if r dot v is less than 0, then we have r dot is less than 0. Notice these are not actually equal to each other. We're just measuring that relative angle. Okay. So if velocity vector is pointing that way versus that way, that's what we're looking at. Aligned or anti-aligned, opposite. So if they're aligned, we're all good because we're in the first arc of the orbit, no corrections required. If, however, we're on the second arc of the orbit, then we do have to do a correction here, 360 minus f, because we're actually measuring this angle. Right. So that gives us, again, all of our orbital elements given the position and velocity vectors. And so that completes sort of the summary from lecture 6 and the first step in that progression, the overall arc, going from position, velocity, t naught, to all our orbital elements now, which we now have at t naught. Or I'm using t1. I don't know. I shouldn't be inconsistent. Next step, of course, is to update t2, find the true anomaly at, not t naught, at t2. To do that, right, we can't do it directly. There's like various steps to go through. First step is, of course, to calculate our mean anomaly at t1. To do that, we first calculate the eccentric anomaly at t1, right? And that's given by this formula right here, going from true anomaly to eccentric anomaly. Next, we calculate a mean anomaly at t1. That formula is given by the easy version of Kepler's equation. Right? So we just plug in there. And now we've got the mean anomaly at the initial time. Right? So good. That's step 1 of step 2, I guess you could say. And now we've got to calculate the mean anomaly at t2, which is on the next slide. So in particular here, I'm back to using t-naughts. So actually, let me, you know what, just because I'm lazy, let me just do cut and paste here. Okay. So, right, now we've got to do this step right here. So T2, let's say, and T1. So the updated mean anomaly is the initial mean anomaly plus n delta t, where n is, of course, mean motion. Formula for that not given here. I think it was like square root of mu over a cubed or something like that. Ah! That was a very bad scream on my part. Undo that. Okay, so now we've got mean anomaly at T2. Next step, calculate eccentric anomaly at T2. Again, this is lecture 4 and 5. Here we've got to solve Kepler's equation the hard way, right? So we're given, in this case, mean anomaly at T2, and we have to calculate eccentric anomaly at T2. Here we have to do iteration, Newton iteration. Next step, a little bit easier. Given eccentric anomaly, we just use this formula here to calculate the true anomaly at T2 and write it down. So now we've completed our arc. We've found our true anomaly at time 2. And the last step, which is the subject of this lecture, if I wasn't spending so much time rehashing all the previous lectures, would be to calculate, translate that initial true anomaly, all the other final true anomaly, all the other orbital elements are frozen, remember, so they don't change. So use these orbital elements and the final true anomaly to calculate the new position vectors at time 2. So that is, of course, the subject of part B. So I'll stop here, give it a break, and then start up.